because we can literally build this from the ground up, we know exactly where everything is. So we have control over all the parameters.
This flume was built in 1973. It was built by the consortium of dredging contractors together with Rijkswaterstaat.
The water soil flume combines soil and water, which makes it very special. Because the combination of the effects of soil and water, if you apply that on structures, you can think of dikes or roads or railways or even monopiles for wind farms. That is what is suitable to test in the water soil flume. The operation at sea is very costly, very expensive, with a lot of risks. And the ideal situation here is to create the conditions and test them here.
At the back is the lorry with the cutter, and we can drive with that one from 1 millimeter a second to 2.5 meters a second. Yeah. When we go to the backwards here, then you see the conditioneringswagen. That's a lorry is there with vibrating needles. You can run over it, you bring in sand and you can compact it till the size you want to have it. Also you see a glass wall there. It's divided, you can put it in between. So it is also possible when you go in with the testing, you can look at the bottom of the flume and you can look through the glass sideways to the test area. Later to the back there's the clay factory. The clay factory then can make clay. You bring it in and you can make a complete, instead of sand, you can make a total area of clay.
My research is often about dredging processes and the interactions between turbulent flow and sediment. So how the flow will excavate, loosen soil from the bed, and how that will generate the density current and plumes.
And they have just polluted the ground and we don't know that they're there. But we have to remediate that, of course. So we have to make sure, also for our groundwater safety, that we know that our soil is unpolluted. So if we can detect and map where it is, then we can actually do something about it. Like a doctor can use a CAT scan to look inside the body of a client, that in the same way or a very similar way geophysicists looked into the soil, into the ground. But we use slightly different methods for that. For instance, electrical resistivity, but also we look at echoes that return from the ground. A lot of the work that we do is also for internal research that we actually do. But that's always where it starts. So we bring solutions up in a TRL level, and then it becomes much more important for clients.
After the client proposes the problem to us, we discuss it and simulate it in GeoSim to find different solutions and methods for a problem. And the third step is to make the actual situation in the water soil flume. We create different clay and sand layers. We control the water level in the setup and bury different types of cables, different types of pipe to simulate the problem and see how we can solve the problem. The temperature measurements are done by glass fiber. This glass fiber reacts with the heat and slightly expands or contracts. With a laser we can detect those expansions and contractions and relate them to a temperature change in the subsurface.
Our aim was to investigate penetration of monopiles through scar protection layers. And the reason why we did those tests was to improve the economic viability of projects and cut down the carbon emissions associated with offshore wind development.
Overarching goal of the project is to investigate alternative methods of installation of monopiles offshore, alternatives to the conventional method, which is hammering down the piles into the ground, and also to understand how the different installation methods affect the lateral bearing capacity or lateral resistance of the piles.
External parties, for example, windmill parks or buried cables at sea, can also benefit from the experiments here in the water soil flume.
together with dredgers, with the ports and universities.
In terms of academic partners, we have TU Delft, and industrial partners include companies such as Vattenfall, Herma, Jan de Nul. And what we are trying to do is to prove that this technology can be applied, and if we find out that this is viable, then we want to roll it out for the wind developments.
And one of the big advantages of the water soil flume is that we have quite a large scale, which allows us to perform the experiments in very realistic conditions. So this vibrohammer, for example, was provided by Cape Holland, which is a company that also provides the vibrohammers for offshore installation. By executing the tests here at the water soil flume, we can make sure that we scale things down in a realistic manner, and also that the scale is not too small.
First and foremost, we have the excellent technical help that we get here. It's solution-oriented, our colleagues. We had some project-specific instrumentation challenges, so we have also colleagues here who have information or who have experience on instrumentation aspects. So together with them, we have found unique solutions to our instrumentation challenges.
For me, the biggest advantage is that the water soil flume is big, so you can do experiments on a large scale, so you don't have scale effects ruining the results, because sediments are very difficult to scale. So that's a big benefit, and it can handle the interaction of flow with cohesive sediment.
We have a reaction frame which is able to move up and down with displacement control, which means that we can insert something into the soil or we can retract something from the soil, which gives us the capability to realize penetration tests. And the length to width ratio of the flume also allows us to do streamline tests, almost automate the tests, so we could do several tests in quick succession. That also helps us because there is a rail system here, so the multi-purpose wagon moves along it. If you imagine the setting where you are doing several penetration tests, then what happens is that you do one test in one location and move on to the next and realize the other. So it's almost like it's automized.
Another functionality in the flume that we used was the crane, and the crane was very important because all the equipment that we used during the experiments was quite heavy. So the vibrohammer, for example, is 600 kilograms. It has 2.5 meters in depth, which allowed us to install piles with 2 meters in depth, 1.5 meters below the ground and 0.5 meter above the ground. So it's a reasonable scale to execute these tests.
The impact of this research is that we can investigate processes to optimize production, to have less emissions, lower costs for the energy transition, for maintenance dredging, those types of applications.
If successful, the project will pave the way for reducing the cost of offshore developments and also increasing their competitiveness.
Climate change brings the effect of other temperatures, extreme cycles of moist and temperature. If we could apply that on the test facility here, if we could add that, that would be a benefit.
When you've seen the interviews here, you may be interested to do some testing here. Feel free to contact us.